welcome. We've talked in previous videos setting the stage for these types of one-dimensional kinematics problems. So we've introduced and discussed position and displacement. We've introduced and discussed velocity and average velocity, and we've introduced and discussed acceleration and average acceleration. We're going to now focus on constant acceleration problems in one dimension. So again, we're going to simplify these types of problems to make them solvable at an introductory level, and then we're going to add complexity as we move on. Right now we're going to focus on one-dimensional problems, and we'll worry about two-dimensional problems in the next chapter. We're going to talk about constant acceleration problems, problems where the acceleration doesn't change with time. That's what constant means, not changing with time. So constant acceleration just means it has the same acceleration throughout the whole problem, or some part of the problem has a constant acceleration. Now, the constant acceleration is typically not zero. If the acceleration is zero, velocity doesn't change. If velocity doesn't change, the problems become actually fairly trivial to solve. So these are constant accelerations, typically not zero accelerations. So some constant positive or negative acceleration in some direction over time. Now, the reason we restrict our analysis to constant acceleration is that if the acceleration is variable, we can solve these problems as physicists, but we require calculus. This class assumes that you do not have calculus. Now, some of you might have been in calculus or have already had calculus, but that's irrelevant. This course is an algebra-based physics course, so we're going to restrict our analysis to constant acceleration problems, which can be solved algebraically. Now, big assumption here, then, is constant acceleration. In constant acceleration problems, the average acceleration, which is noted by the little bar on top, the average acceleration is equal to the instantaneous acceleration. If the acceleration is constant, then it doesn't change with time. This holds true. And a way to think about that is with velocity. If I drive at a constant velocity of 65 miles an hour, my average velocity will be 65 miles an hour, and in each instant my velocity will be 65 miles an hour. So that doesn't change. So the average acceleration is equal to the instantaneous acceleration in these problems, and that instantaneous acceleration is constant. Now, I'll be showing you a set of equations in just a moment, but we're going to change the nomenclature slightly, the notation slightly, of the previous discussion for time, displacement, and velocity. So time, we talked about the change in time from some final to some initial point in time, but when we talked about time, we talked about how our initial time is usually going to be set to 0. So our final time we can think of as the time elapsed. So the elapsed time is just going to be equal to t. We're going to assume for this that at the start of motion, the time is equal to 0. We're also going to replace delta x, the change in position, or this is the displacement, is going to be equal to x minus x naught. Instead of, I used to have x sub f here, x final minus x initial. We're not going to say final anymore. We're just going to place an x here. This represents the position at time t. X naught represents the position at time t naught, which we assume to be 0, t naught to be 0. So x naught doesn't have to be 0, but it is the position, the initial position at time t of 0. And then the velocity, we're going to do the same thing too. The change in velocity is going to be equal to some final velocity, but see how we're not putting the subscript sub f down here anymore, minus the initial velocity. Again, this is the velocity of the object at time t0. This v here is the velocity of the object at time t. All right, here is a list of 5 constant acceleration equations that you can find useful when solving these one-dimensional kinematics problems. So let's go through them. So again, these are constant acceleration equations, which means they're only valid if the acceleration is constant. If you have a situation where the acceleration is not constant, you cannot use these relationships. Of course, in this class, we're not going to look at those types of problems where the acceleration is not constant. But if you do move on in physics and deal with more complex problems, realize that these equations have a limitation. You can only apply them when the acceleration is constant. Now, the first one, equation shown here in green, tells you what the position of an object is at some time t, depends on its initial position and the average velocity of the object. So, there are 4 unknowns here. If you know what the initial position is of an object, you know what the average speed is of that object, or the average velocity, and the amount of time that object has been moving, you can determine what the final position is. Of course, algebraically, you can rearrange this equation to solve for any of these 4 unknowns. This is right now solved for x, but it would be quite trivial, algebraically, to solve this for x naught, or to solve this for the average velocity, or to solve this for the time. You should be comfortable with your algebra skills to be able to manipulate this equation to solve for a given unknown. So if I give you everything in here except t, you should be able to rearrange this equation to solve for t, plug in those values, and solve for t. Now note this other column over here, the missing terms. What terms are missing from these equations? The first missing term here is acceleration. This equation doesn't have acceleration in it. It doesn't have final velocity, and it doesn't have initial velocity. So if you're asked to find the final velocity, this might not be the equation you want to use. If you're asked to find the acceleration, this is definitely not the equation you want to use. Acceleration is not in this equation. It will not give you the acceleration. Second equation is just what is average velocity. Average velocity is initial velocity plus final velocity over 2. Again, only holds if the acceleration is constant. We have here defined average velocity. Fairly straightforward. Again, missing terms. There's no acceleration in this equation. There's no final or initial position in this equation, and there's no time in this equation. So this equation is useful to go from a final velocity or initial velocity to an average velocity or vice versa. Third equation shown in pink here. Final velocity is equal to the initial velocity plus the acceleration times time. Notice how format-wise it's very similar to our first green equation, but instead of position, it's talking about velocity. This is not necessarily average acceleration because remember these are constant acceleration equations, and average acceleration and instantaneous acceleration are the same in these problems. Things that aren't represented, notice that there's no displacement. So there's no initial position, there's no final position, and there's no average velocity. Shown in blue, our fourth equation, the position at some time t is equal to the initial position plus the initial speed times time plus 1/2 the acceleration times time squared. So this actually is probably the most complex equation we will have so far. The only thing missing from this equation is the average velocity and the final velocity. So this combines position, velocity, and acceleration all in one equation. Note that time here is squared. And we'll talk about this equation in more detail in just a bit. And then the final equation, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the quantity of the displacement, which is final position minus initial position. The only thing missing from this lower equation is the average velocity and time. So there's no time in this equation down here. What equations do have time? Well, equation 1, the green equation, has time in it. Equation 3 has time in it. Equation 4 has time in it. In fact, time is a quadratic in equation 4. So if you need to solve for the time it takes something to move, those are probably the equations you're going to want to look at. And we'll talk more about that when we talk about problem-solving techniques in the next video. The thing to remember for these terms is that they use SI units, right? So position is in meters. Velocity has to be in meters per second times time in seconds. Meters per second times seconds gives you meters. Meters plus meters is meters, right? when you add terms in physics, they have to have the same units. Right? They have to have the same dimensions, like length. You can only add lengths to lengths. Adding lengths to time means nothing, right? What's 5 meters plus 3 seconds? Well, that makes no sense. You can say what's 5 meters plus 5 miles, but it's not an easy, you can't just say it's 10 mile meters. That makes no sense. You have to convert the units to be the same throughout a problem, and we typically convert to SI. For this lower equation, you have position in meters is equal to initial position in meters. So each of these terms should be meters. Initial velocity is meters per second times seconds. Meters per second times seconds is meters. Acceleration. Acceleration is meters per second squared times time squared, so that's seconds squared. Meters per second squared times seconds squared gives you meters. So this term is in meters. So meters plus meters plus meters gives you meters. So these equations are very important. Keep track of them when doing these problems that I've assigned, because sometimes you won't find a single equation that matches what you need, but you can use one equation to get an unknown and then plug that into another equation to get your final answer. So some of these problems are multi-step problems.